both in theory and also its applications. Yeah. In this opportunity, he will share some applications and maybe also a little bit about the theory of statistics and maybe some related course. And maybe this is a little bit advanced, but you don't have to worry, because I think the most important thing is we understand that mathematics is very important and beneficial for our life. Yeah, so the time for the presentation is around 50 minutes. 50 minutes. So yeah, so the time is yours, please, Professor Agus Salim.
Thank you, Dr. Diki, and the organizers of this Global Learning Program lecture series. It's definitely a pleasure for me to be here today to share a little bit of my experience as an applied statistician in the middle of this big data explosions in biology that has been happening for the last 10 to 15 years. So I hope the students will learn something out of this lecture. As Dr. Diki mentioned, some of the concepts could be a little bit advanced, and there will be lots of biology that I'll be talking about, a lot of biology that probably outside your comfort zone as a mathematics student. But the my objective of showing you this is to really share with you what is actually required to be an effective applied statistician. I mean, if you want to make an effective contribution to other fields. Okay, so understanding of concepts in other areas, it's really, really crucial. All right, so I'll start my lecture with sharing you my screen. Sorry for the delay. It's my old laptop crashes 2 days ago, so I'm now on the new laptop, and I'm still getting used to my new laptop, all the setting. And can you all see my screen? Can you see it now?
Yes, yes, you can see your screen.
All right, good. Okay, so if there's anything amiss, that I mean, you know, you want to follow it up, and you something that's not working, just let me know. All right, so the title is Mathematics for Life. Yeah. So this is the outline of the talk. So first, I'm just going to briefly go through what I call the big data era in biological science that has been happening for the last 10 to 15 years. And then I'll talk about a case study that I'm hoping or more specific. We'll finish with conclusions. All right, so this is a figure, okay? You can see on the x-axis is year, right? And on the y-axis is the number of human genome that have been sequenced. Now, what do you see here is that prior to about 2010, right, or 2009, 2008, there are not so many human genome that have been sequenced around the world. But since then, you can see there has been an exponential growth in the number of human genome that have been sequenced. So when I'm talking about human genome, it's the whole totality of DNA of a person, okay? From the first base in chromosome 1 to the last base in chromosome 22, plus the sex chromosomes. Yeah. So from 2008 to 2009, there has been an explosion in the data, in the genomic data that have been sequenced. And to understand why, you see this, if you look at this figure, the curve is almost the opposite. The pattern is almost the opposite of that one, of the previous one. Where here, you see that around 2008, what happened there? There is a drop in the cost of sequencing per genome. Okay, so if you see, the first human genome was completed around 2001, 2001, right? Joint effort between what do you call it? Between the U.S. government and Eric Lander. So at that time, you can see it cost about $100 million to sequence one genome. So it was not accessible at that time for a lot of, not only lab, but for a lot of countries maybe around the world to, to sequence even one human genome. And around 2008, there is this new technology called next generation sequencing. So I'm not going to go into detail what is this next generation sequencing and what differentiates this new technology to the previous one, which is called Sanger sequencing. But it's enough to say that the new technology allow you to sequence a human genome faster and, more importantly, cheaper. So if you look at 2015, you can reasonably sequence a human genome for about $5,000. Yeah. So this opened a lot of avenues for a lot of labs around the world. Now they have access to this technology. They started generating data. They want to understand how, let's say, specific mutations are linked to certain disease. Yeah? How can we cure cancer, for example? Because cancer, at the end of the day, it's this disease of the DNA, I call it. Okay, something happened to the DNA that causes cancer. All right, so I'll skip this thing. This is I'm talking about storage, but I think it's not as important. All right, so how can statistics play a role here? Well, first, let me tell you, the data volume is massive. Okay, we are talking about 100 gigabytes to several terabytes if you're doing a complete genome sequencing per person. So the data itself is very big. Yeah, this is where biologists, because they are not trained, in a kind of a very quantitative manner, at least until about 15 years ago. The quantitative curriculum if you're taking a biology undergraduate program, for example, the quantitative curriculum is not as strong as the non-quantitative curriculum. They will need a lot of help in analyzing this kind of data. Okay. Secondly, the data quality is often not great. So you have a lot of data, yeah, but the data has a very low signal to noise ratio. So you can imagine it's like, when I say low signal to noise ratio, you can imagine it's like looking at a blurry picture. Okay, so you have a big picture, yeah, but it's all blurry, right? And there are also a lot of biases in the technology. Yeah, the technology is not perfect. You think it's supposed to do what it's doing, but it's not. And we will see in our case study. So, of course, improving, signal to noise ratio, removing bias, that's the job of a statistician. Yeah, so that's where we can actually contribute as a statistician. All right. Now, the specific thing that I want to talk about today, the case study that I want to talk about today, is something called single cell technology, right?
Now, in the last few years, we now have the capacity to sequence not only a genome, but also sequencing each cell separately. So you think about if you go to a doctor, right? The doctor will draw your blood, yeah, for blood testing. Now, inside that blood, that small kind of volume of blood, there are thousands, even hundreds of thousands of cells. The single cell technology will allow you to sequence each of that cell separately. Yeah. And the cost of sequencing this cell by cell is actually not very expensive. We are talking about 25 cents. For $1 for 4 cells. Yeah. This technology is very, very hot. It's a very hot topic. It has been used to find new cell types. Yeah. And it has been used in finding kind of a new therapy for disease like cancer. Okay. The nice thing about this technology is that not only you can sequence each cell separately, you also can barcode each molecule in the cell. Imagine you put the barcode to each molecule, okay, using this technique called unique molecular identifiers. Okay, so you know at the end when you sequence it, you know the identity of each molecule. Yeah, of course, this is all done. Okay, they are adding the molecules and also adding spike in. So spike in is actually like artificial genes that you add into the samples. Okay, all of this is done by robots. Okay, so very quickly, this is how the technology works. Okay, you often you sort the cells, okay, and the cell will have to go through this kind of machine or this kind of machine where it will be sorted one by one, captured by this kind of oil solution, okay, and made into droplets. So that's how they separate the cell, and the cell then will go into this kind of plates, okay, where in each well here you have one cell, and then they will be sequenced one by one separately. As I said, it's a hot topic. You can see that there is an exponential increase in the publication using single cell data in the last few years. All right, so the case study that I want to talk about, it's about breast cancer tumor, specifically a T cell. So I'll introduce a concept here. So there's something called a tumor infiltrating lymphocyte. Okay, so these are the lymphocytes that can actually, you know, we're talking about a lymphocyte like white blood cells, okay, that can infiltrate tumor. Okay, you know, white blood cells is involved in the defense mechanism, right? This one is very successful. It can actually infiltrate the tumor. It can stay in the tumor. So obviously, if you have a lot of tumor infiltrating lymphocyte, you know, your chance of survival often is very, very good. Okay, I'm going to skip this slide. This was meant for biologists. All right. So one of these tumor infiltrating lymphocyte is called tissue resident memory T cells. You know, T cell is involved in defense mechanism. So if your body is infected by virus, for example, then, you know, T cell will come to the fore, especially a CD8 T cell will come to the fore to try to defend your body. Now, if T cell encounter a foreign, let's say, a foreign matter, like it will identify that as an infection, and it will actually learn from that episode. Okay, and this is why a lot of if you say if you get flu, for example, then you will develop immunity because well, your T cell will actually learn about the virus contained in the in the flu, and next time you get something similar, your body will act quicker. Okay, so there's some kind of memory of the T cell. Okay, the T cell retains some memory about the past infection. Now, most of these T cells are actually in the blood. Okay, the T cell that has this memory, most of them are in the blood, but some of them are actually in the particular tissue where the infection has taken place. That's why it's called tissue resident memory T cell. So, for example, people who had, say, problem with their breast, they have breast cancer, there will be some tissue resident memory in the T cell. Sorry, in the breast. Okay, and the more tissue resident memory T cell that you have, the better it is, right? Because obviously, if you have a lot of tissue resident memory, when your body is attacked by the same kind of agent, it will be quicker for you to recover, and it'll be easier for you to defend. Yeah, but the strange thing is that people differ in terms of their ability to retain this tissue resident memory T cell. Some individuals have a very good ability to retain the memory. Others are not, right? So this explains why some people can get infected again and again, and others can become very immune just after 1 or 2 infections. Right now, what I want to talk about is specifically here is the role of tissue resident memory T cell in the triple negative breast cancer. Okay, so triple negative breast cancer usually have a very bad prognosis. Okay, the survival is very poor, but some triple negative breast cancer patients survive much better, and we want to understand what differentiate these individuals that survive longer compared to those who survive shorter. Yeah, and you will see that T cell, tissue resident memory T cell, will be involved there, and that would explain why some these people actually survive longer than the others. So the data that we have come from 2 individuals. They both have triple negative breast cancer. Yeah, so we perform single cell sequencing. We take their RNA, okay, of each cell and sequence them using the technology that I mentioned before. Okay, adding the UMI, barcode, so you know which molecule, each of the molecule identity. Okay, and you also add the spike ins. This is how the data looks like. Okay. Now we don't know. Obviously, this is from 1 patient only, case number 1. Yeah, you can see there are clusters there. These clusters correspond to different cell types. Okay, because remember, we take this biopsy out of the patient breast, but when you take a biopsy from a breast, there are a lot of cells. And there are different cell types, just like blood cells. Okay, there are red blood cells, white blood cells, and so on. Here, the same. You got a lot of different cell types. So the clustering here. Okay, so we got the data, and we visualize the data in a 2-dimension visualization, and you can see the clustering. But we don't know what each cluster corresponds to in terms of the cell types. Okay, but we suspect that some of these clusters actually correspond to what's called tissue resident memory T cells. Okay, because these people, these 2 individuals actually have a very good survival, so they must have a lot of tissue resident memory. Now, with that thinking, we started looking at the looking at some markers of this tissue resident memory. each cell type has their own signature, okay? Just like a human being, you have your own signature. Each cell type also have their own signature. So tissue resident memory T cell have certain genes where you know their kind of expression or their molecules will be more abundant than for other cells. Here, I mean, you can see that these are a tissue residence memory marker. You can see that this cluster, for example, is very high. Okay, red meaning high. Okay, and gray meaning it's low or it's not expressed at all. So we don't have molecule coming from that gene. You can see that for some TRM markers, we can kind of guess which of this is the kind of the cluster corresponding to the tissue resident memory cluster. But if you look at other clusters, other markers, this one, for example, there is nothing. Okay, there's nothing. So if you just if you're basing your decision on annotating the cluster based on this particular marker only, you wouldn't know, right? It's zero everywhere. That one very small. Okay, this one is not too bad. This one again, I mean, you can see that a lot of these markers we have failed to capture any molecule that come from that markers. Okay, that make us kind of fail to differentiate the tissue resident memory T cells from the rest if we use only those markers. Now, to understand why we do not observe a lot of this molecule, okay, we then need to go back to the technology. Okay, the technology works as follow. Okay, you take an RNA molecule from a cell, yeah, and then you apply what's called a reverse transcription process to turn this molecule into cDNA, yeah, and then you amplify the cDNA, and then you sequence them. Now, this step here, the reverse transcription process is far from being perfect. Okay, so you lost a lot of molecule in that step. Yeah, so let me say, if you have 100 molecule here, maybe you only able to turn 10 of them into cDNA. So there are a lot of molecules that are lost. Yeah, which mean that if you're seeing zero everywhere here, it doesn't mean that they are really zero. Yeah. So we need to be able to somehow, we want to be able to see what the number of molecules look like, okay, here before all of this process is done. Because at the moment, what we are seeing is the number of molecules here, right? At the end, when the sequencing is done. We want to see what's the molecule is there. Okay, the number of molecules there. Now, how do we do that? Okay, there are some approach to do that, including something called MAGIC and SAFER. You can look at this paper, but we also develop our own kind of imputation approach. All right. So these are the markers that we have, okay, before and after imputation. Now you can see here, this is before imputation, and this is after imputation by SAFER. That's before imputation. This is after imputation. So you can see what the imputation has done is it actually replaced the number of molecules that we observed here, if I ask you where is the cell populations that actually express this marker, you don't really know here, for example. Safer man two genes, when the data are not imputed, the correlation is not very clear. But here, look at it. It's very, very clear. Here it's not very clear. This one, you get a negative correlation. And this negative correlation is actually confirmed by the biologists that these two genes supposed to work in the opposite way, right? So imputation works, kind of helps a lot in this case, okay, to kind of undo the effect of the unperfect or imperfect technology, right? Now, I mentioned about Magic, I mentioned about Safer. Those are the imputation tools that you can use. But we also developed our own imputation tool called DESCENT. Okay, so DESCENT is actually not a general imputation tool. It is used for something called differential expression analysis, but I'm not going to go into the detail, but I'm going to show you how we built DESCENT. Okay, first, it comes out of this framework that what we are observing, okay, the data that we are observing is at the bottom here, okay, and on the last kind of row here, okay. So you can see that a gene can be either silent, not being expressed, or it can be expressed. All right. So if the gene is not expressed, of course, I mean, you will get 0 count from that gene because, you know, no molecule of that gene will be captured. But if the gene is expressed, you may still not able to capture any molecule out of that gene and end up with 0 count anyway, right? So this is a problem of differentiating. If you have a 0 count, you don't know which of the 0 count is real 0 and which of the 0 count is actually technical 0. Okay, so when you're performing imputation, yeah, you need to impute this, what I call technical 0, fake 0, but you should not impute the biological 0 because they are the real 0. Yeah, so that's one principle behind our imputation. You impute only the biological, the technical 0, but not the biological 0. Yeah, obviously, to be able to do that, you will need to be able to differentiate which one is the technical and which one is the biological 0. Okay, now to be able to differentiate the technical from the biological 0, we need 2 models. First, we need a model. We need to model the process in which the molecule drops out, the molecule fails to be captured. Okay, now here is this is from Spikin's data. Okay, Spikin genes, and you can see that there's a very nice curve here. Okay, so here is on the y-axis, that's the proportion of cell with 0 count. Okay, and that on the x-axis is the log concentration of that particular gene. So you can see that if the gene is very abundant, it has a lot of molecule. Okay, it is less likely to have zero count. Okay, so genes that have low kind of number of molecules to start with, okay, low concentration, they're more likely to have zero count. So the probability of technical zero, okay, depends on the concentration of the gene. That is for one, right? So we tried, at first, we tried this model. We tried this model where we say, okay, Z here is our observed count, okay, and Y is the original count, okay, the original number of molecule, and this is the observed number of molecule. We say that the process is binomial. So if you have Yij number of molecule in the beginning, and each molecule can be captured according to this probability, okay, then the number of observed molecules follow binomial distribution. Yeah, this is an assumption. So one thing that's important to note is that as an applied statistician, you need to check all of those assumptions. Okay, so you can come up with a model, but you need to check how good your model is. Yeah. So that's one very simple kind of molecule dropout process where we say, all right, if you have, say, 10 molecules in the beginning, then you know the probability of capturing each molecule is, say, 50%. Then you know the observed number of molecules will be binomial with with size parameter Y here 10 and probability of capture 0.5. Okay, now we want to test the feasibility of how good is that model that we just conceived. Okay, and we will test it using this 7 real data set. Okay, so we have this 7 real data set where we have spike-ins. So we know how the molecule concentrations in each of this data set for the spike-ins, and we also know how many technical zero each spike-in gives you. Okay, and as a competitor, okay, to that simple binomial dropout model, we have this dropout model where instead of using binomial, we use something more sophisticated called beta binomial. Okay, I'm not going to go into detail what's the difference. So there are 2 different models. The beta binomial is slightly more sophisticated than the binomial one. So here, all right. So let's see the result. Okay, red one. Okay, sorry. We talk about the gray one first. Okay, the gray one is the observed data, and red one is the predicted the prediction according to the binomial model, and the blue one is the prediction according to the beta binomial model. Okay, so this, you can see here that the beta binomial model actually fits the data very, very well. Okay, so this is why I said that we always need to test the assumption that we make about models. So we can come up with a model, but we need to test that empirically. You can see here that across a lot of the data set, beta binomial is not perfect. Like here, it's not perfect. Here, it's not perfect, but it's better than binomial, A, and B. In some data sets, it's actually quite good. Yeah. So this is where our decision to use beta binomial dropout model for the molecule dropout process comes from. Okay. So we have now the dropout model, the molecule dropout model. But we also need, so 2 things that we need. We need the molecule dropout model, and we got that. But we also need the probability distribution for the pre-dropout molecule. the original number of molecules that we do not observe, right? And for that, we choose this what's called zero inflated negative binomial distribution for the pre-dropout distribution of the molecules. Okay. And why we choose that, we also have some empirical evidence why we choose this. As I said before, you can make an assumption, but then you need to back it up by some empirical evidence. So we have some empirical evidence. I think I'm running a bit out of time. I'm not going to go through the detail, but this empirical evidence supports our choice of using zero inflated negative binomial for the pre-dropout count. Okay. All right. So what do we have then? We have a pre-drop distribution, okay, a probability distribution for the pre-dropout count, and we have this conditional distribution of the observed count given the pre-dropout count, given by the dropout model. Okay, so this is the dropout model, the beta binomial, and the pre-dropout count. Okay, and what we need to do then is we use something called EM algorithm. Okay, so you have to go in iteration to perform your estimation. But what you need to do is actually, if you want to impute, right? If you want to impute, what is imputation actually? Imputation is replacing the observed count, okay, with your best guess of the original number of molecules, right? So using this two specified distribution, okay, of course you need to estimate the parameters associated with this distribution. That's why we use EM algorithm to do that. But the step inside EM algorithm, okay, actually has kind of some imputation steps. Yeah, the imputation steps would require you to take the expected value, okay, of the original number of molecule, right, given the observed molecule. Yeah, and it also required you to calculate the probability of zero being a technical zero. Okay, so these two things are the quantities that you calculate in the E step of the EM algorithm. Okay, why do you need to do that? It's because you do not actually observe Y. Okay, so Y is in a way is missing. It's your missing data. The data is completely missing. Okay, what you observe is Z. Yeah, so that's why we need to use something like EM algorithm, because what we have here is a missing data problem. We have a missing data problem. We are trying to estimate Y from what we observe, which is Z. Okay, because of that, you cannot just use a maximum likelihood or any other kind of a straightforward estimation parameter estimation procedure, but you need to use something like EM algorithm, while the estimation of the parameters, okay, is done simultaneously while estimating the missing data. Yeah, so the missing data here is the Y. Okay, so you do this until you achieve convergence. Yeah, so here is the output of DSEN. I mean, some output of DSEN. You can see that here before imputation, okay, the counts between these two individuals, for example, are very similar. We fail to differentiate these two individuals based on this gene only. But after imputation, you see a much better kind of separation between the two individuals. This is an example where imputation actually improved this signal to noise ratio. Okay, but we don't stop there. We also use DSEN to perform what's called differential expression. So we want to be able to identify what are the genes that are different in each of the cluster. Okay, so when we apply this to our data, to the first patient data, we managed to find that these are the list of genes that differentiate each of that cluster. Okay, so you can see that one of this cluster is called CD8-TRM. Okay, so this is the CD8 T cell that have tissue resident memory kind of characteristics, and the other cluster is called CD8 T cell effector. So those are the CD8 T cells that do not have the tissue resident memory quality. All right, so let me make a statement again here. So using this, we are able to identify the signature or the clusters that harbor cells, okay, that exhibiting properties of CD8-TRM. Okay, so this is for the second case. Basically the same thing. We applied this and we also found those CD8-TRM clusters. Okay. Now, how do we know that what we are doing here is right? What Deason has found is correct? Well, for that we need to compare what Deason has found. Okay. So, using single cell data to what was found by other researchers, okay, using bulk data. Okay, so let me tell you the difference between the bulk and the single cell. The bulk data, okay, that's when you sequence thousands of cells at once. You don't separate the cell one by one. And because you have a lot of molecules, when you have thousands of cells, there are very few there are very few technical zero occurring. Okay? So with bulk data, you don't need to with single cell data, there are a lot of zero counts. You somehow need to take into account the fact that not all molecules. Now, these are trying to perform differential expression analysis while using the same time. If Deason is successful in performing computation, Deason, the gene that has been identified by Deason itself should agree very well to what we found in the bulk phase. Alright, so here is what Deason has found. Okay. This is called volcano plot, because it looks like a volcano. So the red and the blue ones are the genes that Deason had found to be differentially expressed between the CD8 T cell that have TRM properties and CD8 T cell that do not have TRM properties, right? And here, I mean, I'm sorry, it's a bit small. You can't really see the name. But if you can see the name, the gene that that were found here by the bulk, a lot of them were actually found by Deason as well. So there's a very good concordance between the result that Deason found, okay, using single cell data with a lot of dropouts to the result that you found using bulk sequencing technology, where there is no dropout, and you don't need input. So that's this concordance. We take it as an indication that Deason imputation has been very successful in recovering the biology. Okay, and not only that, we take this list of genes that Deason has identified, and then we go back to a a cohort of breast cancer patients and calculate what we call their TRM score based on their expression of these genes. Okay. What we see is that people, okay, the green one is people in the cohort, okay, 60 people where their CDF TRM signature is high. Okay, so this means that these individuals are very, very likely to have a lot of CDF TRM. The purple one, 23 individuals that have low signature of CDF TRM. So they're very they are less likely to have a lot of CDF TRM. When we compare their survival curves, what do we see? We see that the survival for the survival for people with I think I made a mistake in terms of all right, so okay, I got it. So we'll be comparing these individuals with high CDA, okay, signatures, and also high tissue resident memory signature. Okay, that green curve there, that green survival curve. And then there's the green dotted survival curve where they have high CDA signature, but in terms of TRM signature, it's not very, very high. And you can see that people with high TRM signature, that means they have a lot of tissue resident memory, they survive better. The survival curve stay higher much longer. Okay? And the same thing if you compare with this purple one to the dotted purple. Okay, so this indicates that again what Dixon have found here, okay, in terms of the list of genes, actually have a lot of kind of biological relevance. Right. So I hope before I finish, I hope that what I have talked about today demonstrated to you the potential basically of mathematics, or more specifically statistics, to drive discovery and also progress in biological science. And secondly, to be most useful, okay, to be most useful, mathematicians or statisticians need to collaborate and learn about other fields. I mean, you notice during my talk today, I refer to a lot of biological concepts. Now, I do not have a degree in biology, but I learn about the biology by collaborating, by talking to the biologists, okay, in at least weekly basis. We meet and we talk, so we understand what are the problems. Because while mathematics has the potential to drive discovery and progress, we need to understand what are the problems that our biologist colleagues are actually facing, so that we can make a relevant contribution. Okay, so and I like as a final slide, I'd like to thank my collaborators, so Terry Speed at the Walter and Eliza Hall Institute here in Melbourne, Australia, and Cheng Chong Ye from Tsinghua University in Beijing in China, and Peter Safas and Shirin Loy, the owner of the breast cancer dataset. Thank you.
Okay, thank you. Thank you very much, Professor Agus Salim, for the lecture. I think it is amazing that you delivered a talk about big data in biology. I think big data is one of the most hot topic fields in the last few years. Okay, now it's time for discussion. Anyone wants to ask to Professor Agus Salim? Do you have any questions? It can be related to the topic or a little bit not related, it's also fine. Maybe you have
Yeah,
some.
I think if you don't want to kind of ask the question directly, you can just type it up in the chat. I mean,
Yeah,
I can check my chat.
Yeah.
How do I check it? Should I stop sharing my slides or?
Yeah, you can stop share the screen.
Okay, now I can see the chat button.
Okay. Maybe I will ask first. Maybe after that, the students can
Sure.
continue with other questions. Yeah. So as you already know that nowadays, as far as I heard from some news and also information that the need for a person that is expert in big data are getting more and more. And this, I think this makes the opportunity to find a job related to big data are maybe have a quite high opportunity. Yeah. Since here we have many freshman students, I think they still have a very long way to go to their career. At least they have to spend 4 years in their bachelor study. So maybe you can share, like, if they want to become a data scientist or expert in big data, what kind of knowledge or what kind of skills, what kind of competency that they should build. Maybe they can.
I lost you there, Dr. Dicky.
Yeah, I think he has a problem. I can't hear.
I lost you for maybe about 20 seconds. Could you repeat the remaining of your question again?
Pak Diki tadi sempat putus. Can you repeat, Pak?
Oh ya, sempat ya. Oh ya. Let me repeat it again. Yeah, the internet is a little bit lagging. Yeah. Okay. So as we already know that the field of big data or data science is a hot topic in the last few years. And many industry and many company needs people that are expert in big data and data science. So I think it is also a great opportunity for them to for the students to focus on this subject. Yeah, and now they are the students are now still in the first year, so they are still freshman students. Maybe you could give some hints, like if they want to become an expert in big data, what kind of knowledge, what kind of competency, what kind of skills that they should learn in order to become an expert in big data, so that they can plan their study better. Thank you.
Thank you, Dr. Dicky. I think it's a very good question. It's a very relevant question. First of all, I think all of you probably know about the Harvard Business Review calling data scientists the sexiest job of the 21st century. So if you're not, maybe some of the students are not familiar with that, let me share the screen. Okay, so data scientists, the sexiest job of the 21st century. So definitely there are a lot of opportunity for data scientists, and it's a skill that will be very relevant, you know, for the foreseeable future, because we are, as you see from my talk, we are getting more and more data. Before, so there is an anecdote, right? It used to be like in biology, at least. It used to be that the biologists will take, say, 1 month to generate the data, and it takes the statistician, 1 hour to analyze the data. Now, it's the other way around. I mean, they can generate the data in 1 week, and it takes us 1 month to analyze, because the data is so big, it's so complex. Okay, so it's easier now in a way to generate the data than to analyze it. Okay, so that's just to because of the sheer size, because of the complexity. Okay, because a lot of this data has low signal to noise ratio, so you have a lot of information is true with this kind of data, but they are, many of them are actually, I wouldn't call it rubbish, but I mean, a lot of them are actually not relevant information. So you need to be able somehow to extract the relevant information from this big cloud of data. Okay, and to do that, in my opinion, you need three things. First, you need to understand statistics, right? You need to have knowledge about statistics, because extracting information out of your data, you will be using a lot of machine learning or statistical methods, yeah, and therefore you need to understand statistics, because otherwise you will make mistake. You will make a conclusion that does not represent your data at all, because statistics is about representation. So that's number one. Okay, number two, of course, you need to have knowledge about all this machine learning, artificial intelligence, very good programming skills, basically. Yeah, those are also necessary, because well, if the data is huge, you need an efficient way of processing the data. So you need to understand, you need to have some basic of computer science, programming, parallel computing. Perhaps now we are also reaching a stage of cloud computing. And third, what you also need is the domain specific knowledge. Okay, so like I apply my skills to biology, so I need to understand biology. Not as much as the biologist, of course. I am not a biologist, so I always jokingly tell them that if I make a mistake, that's okay, because I'm not a biologist. But you do need to understand to some extent. You need to have a good understanding, and you can imagine, if you work, for example, in a company for as a data scientist, and you have been tasked to come up with marketing strategy, okay, utilizing the information that you can extract from the data, and you do not understand at all about marketing, you do not understand at all about human psychology, then your ability to be able to make recommendation to your boss, I think it will be less effective. Yeah, so three things, yeah: statistics and mathematics, computer science, and related knowledge, and then domain specific knowledge. And the domain specific knowledge, I think, is a bit harder for you to get it when you are an undergraduate, but you can get it when you started working, when you decide what you want to do to be able to become an expert in that field. Then you need to gather the domain knowledge for that particular field. Thank you, Pak Diki.
Okay, thank you very much for the answer. Yeah, there is a question from the students. I think she maybe write it privately. Let me pass it in the.
Yeah, I didn't see it on my chat window. Oh,
she wants to ask how the scientists predict the date of the end of COVID-19 pandemic. Yeah, I think it is quite actual and relevant question. Yeah.
How can you predict? Well, basically, you can predict, but the prediction will depend on a lot of factors, right? So if you can assume how fast countries basically getting their vaccination program kind of completed, and then if you can assume that the virus are not going to mutate faster than what its current rate, then you can make that certain predictions. But that prediction there's a lot of uncertainty to that prediction. Okay, it depends on those factors that are often beyond science. It's a political factor sometimes, because if you want to achieve, I believe that you need to achieve about at least 70% immunity in the population before you are then able to kind of basically get by with COVID-19. Yeah, there would still be cases, but the cases will be manageable because 70% of people in the populations are immune. Okay, and as you can see from my presentations, even if 70% of people are vaccinated, it doesn't mean that 70% of people, all of those people will be immune, because people's ability to retain immunity varies, right? But I think my estimate will be about 70%. If you can vaccinate about 70% of the people, then then COVID-19 will become a problem like maybe something like flu. In Australia, because we have 4 seasons in a year, we get flu vaccine every year. Yeah, maybe it's not very common in Indonesia, but I mean here we get flu vaccine almost every year to protect ourselves to the new strain of flu virus. So I think it will come to a stage where, when the initial kind of 70% of the population is already kind of already get the vaccination, then you will have this kind of program where getting a COVID-19 vaccination is almost like getting a flu vaccination, where you just need to update yourself every maybe a couple of years, go to your doctors and get vaccinated. Because well, we do that. This is not very common, I think, Pak Diki. I mean, my friends in Indonesia are not so used to getting vaccinated every year for flu. So they were it's something new to them. But for us here, because of the cold weather, the flu can be very bad. So we get vaccinated almost every year. Yeah. So I mean, I know there are a lot of people who are against vaccination for one reason or another. So let me put it this way. I mean, I am not forcing or promoting people, forcing people to get vaccinated. But my view is that until 70% of the people get immunity, okay, either artificial through vaccination or through other natural sources, then I think the pandemic will be under control.
Yeah, thank you. Yeah,
thank you.
You're absolutely right. So in Indonesia, when we got a flu, we just take, I don't know, some hot water and then take more rest, and everything should be fine. That's what we believe. So yeah. I used to be like that. I think when I was younger, but as I grow older, everybody, when they grow older, your body become weaker. Then you realize that that's not enough. I need to get vaccinated, because if I don't get vaccinated, every winter I will get flu, and then I will be in bed for 2-3 weeks, and I have no works done. And if you lost 2-3 weeks, you lost a lot of time. Yeah. Okay. Thank you. Yeah. Any other questions? You can ask directly as well to Professor Agus Salim. You can also ask in Indonesia. It's fine. I think.
Yeah, it's fine. Or in Javanese.
In Javanese also fine. Dalam bahasa Jawa juga nggak apa-apa. Please. Any questions? No. Please don't be shy. Okay. Yeah. Okay. Maybe let me then ask another questions. So this is a little bit maybe more general question.
Yeah.
So as we know that most participants here are still on their first year students. Maybe because they are still in the early stage of the university, maybe you can give some hints on maybe what kind of I don't know, what kind of study technique that or maybe you can share your experience, like how were you studying during your bachelor study or something like that, that maybe can inspire them to maybe successful in their study in the next few years. Yeah, thank you.
Yeah, yeah. I think looking back, when I was, undergraduate students, there were certain things that I think could have been done better from my side, from my perspective. And one thing is that you should follow your interests and your passion. Okay, so whatever your interest and your passion is, you should follow that, and that should determine, let's say, what elective subject that you take. Don't take easy elective subjects just because you want easy, easy mark, easy grades. Yeah, you will regret that later. Take elective subjects that satisfy your curiosity and your interests. So being able to, and of course, to do that, you need to, to be able to identify what your interests are, right? So that's another thing. You need to be able to identify what your interests are early. Yeah, and how do you do that? Two things: read and read. Okay, read more. Yeah. In my days, we read in the libraries. I mean, we go to libraries and we spend hours reading, because at that time there was no online book, there was no ebook. Yeah, Dr. Diki probably know as well. I mean, you just you go there, and there's only one or two hard copies of the book, and if it's already borrowed by somebody else, I mean, you have to wait your turn, right? With ebook, everybody can access and have read at the same time. So things are much easier now, but you need to read, because only by reading you understand what you like and what you don't. Yeah, and follow what you like. Yeah, of course, you have to be. It has to be balanced. Okay, it has to be balanced between your passion and also job prospect. Yeah, you don't want to follow something that have definitely no job prospect just because you're interested in it. I think it has to be a balance, because at the end of the day, you want something that give you reward, and part of that reward is a financial reward. I mean, you don't have to be rich, but you don't want to be poor. I mean, let's put it that way. Yeah. So it has to be a balance between job prospect, but also your interest, and you need to read more and more. First, second, take the opportunity to to discuss with your professors. I mean, I was lucky enough to be taught by the late almarhum Professor Dr. Andi Hakim Nasution. He was amazing. I used to be very scared of him, right? Because, well, he was a professor. I mean, I was only an undergraduate student, so I didn't dare speaking to him. But then one day, I asked him about a problem that I read in a book. I put all my courage just to ask him that question. And amazingly, the next day, he actually brought me a book. He said, read that. It's all explained there. So you see, if you kind of don't be presumptive. Don't be presumptive. Don't assume that professors don't have time for you. They will be very interested in what you're interested in. If you ask them politely, I'm sure any reasonable professor will make time and will be interested in the problem. I mean, that's why they become a professor. I mean, they're interested in the science itself. So if you ask them a question about the science that they're interested in, sure. I mean, there'll be no question. So I guess don't be shy. Be forthcoming. You know, if you don't think, I guess if you have an ideas, discuss that with your with somebody more experienced, because you can have an ideas and you don't work, you have an ideas, but because you're not experienced, you sit on that ideas for weeks, for months, for years without knowing whether your idea is a good idea or a bad idea. But somebody more experienced than you can guide you. They can let you know, is that a good idea or it's not so good idea, or if it's not so good idea, I mean, what way to improve it. I think that is that would be my advice. But perhaps the last one is this: if you do something, okay, there is an American expression, and the late Nobel Prize winner Richard Feynman often say this: when you do something, do it to the hilt, which means that if you want to do something, okay, if you have a dream, work your socks off to achieve that, okay? Don't stop. Be committed and determined to achieve your dream. And dream big. Dream big. Don't be afraid of dreaming. Dream big, okay? Set your target and work towards that target. Okay, along the way, you may modify your target, you may adapt your target, but never give up. Okay, I tell you a little bit my background. I didn't start speaking English until I was 22. Okay, so because I didn't graduate from a senior high school in the middle of a city. I mean, I graduated from a senior high school in the middle of a transmigration area. You can imagine, right? It's a rural area where the way they teach English is using Bahasa Indonesia. So how can you speak English? I couldn't speak English until I was 22. When I had to sit for a GRE test, I wanted to go to the US to study, to do my postgraduate degree. And of course, if you want to go to the US, you had to sit for TOEFL, you have to sit for GRE. Okay. My first TOEFL test, 510. Yeah, that's not good. 510. Well, I don't know what's the score is like now, Dr. Leakey, but I think during my time, you need to achieve like 550 at the very least, or 580. So my TOEFL was low. My GRE, there are a lot of the verbal component. There were a lot of things that I didn't know. A lot of words that I didn't know. I got my GRE was, I think, the analytical part was fine, but the verbal part, I was easily in the bottom 10%. Yeah, because my English was so bad. Then what I did, I decided to, so this is talking about if you have a dream, right? Be determined. Be determined. Don't give up. Okay. You fail once, but then pick yourself up again, and then do it again. So I started reading English language newspaper, pronouncing the English words to myself one by one every morning. And, in a few months, my TOEFL become 600. So you see, that's if you give up, you will never achieve your dream. So when do you know? I mean, when you know that you haven't given your best, okay? Don't give up. Don't give up. Be determined. Work hard, because, okay, while the final our final destiny is not up to us, okay? It's up to God to decide, but we must try our best in whatever we are doing. Yeah, so try your best in whatever you're doing and achieve to the best of your ability. Not everybody must become Bill Gates, okay? Not everybody must become a Jack Ma, but everybody, in my opinion, everybody must achieve their best potential. Thanks, Pak Diki.
Thank you very much. I think it was very inspiring for me and also for the students as well.
No, I think it's because, sorry, I mean, I spoke a little bit about my background because I think a lot of the students, or even I think a lot of people in Indonesia, when they see me, they think that I come from a big city like Surabaya, and I had a very kind of a privileged upbringing and a privileged education.
Yeah.
So that's not the case. Yeah.
Yeah. Thank you. I think it was a real story. Yeah. Okay. True story. Yeah. Any other questions from the students? Any questions? Feel free to ask questions. I think we still have a few more minutes here. Any questions? Yeah. There's a question from Pak Irfan Shah. Monggo Pak Irfan.
Yeah, thank you, Dr. Diki. I'm not a student, I'm sorry, but I hope I can ask a question.
That's okay. Yeah, that's okay.
Well, I'm very impressed that when you said that you do not have a background in biology, yet when you presented your presentation today, you know a lot about genetics, DNA, and sequencing. My question is, maybe for faculty members like Diki and myself, how do we encourage collaboration in the first place? So when we don't know each other, and maybe I myself, I'm from electrical engineering, but I know that we can collaborate with people from other departments so we can achieve more. But how do you do it in the first place? I mean,
yeah, I think we are. I'm lucky. I mean, I'm in Australia, so we have less of a sectoral ego. What you call it? I think in Indonesia that's more prevalent, where people from different disciplines, think that they're, well, I wouldn't say that they think that way, but from what I heard, there's a tendency of one discipline think that they are better than the others, and therefore they don't need the other discipline and so forth. So in Australia, there is that, of course. If you work with doctors, sometimes I find that they, well, I mean, they probably look down a little bit on you because they think, you cannot go to Faculty of Medicine and therefore they're smarter than you. There is that. They don't say it, but I mean, there is that tendency. But it's much less than Indonesia. So I think to start with, I'm lucky that way, that there's much less kind of resistance. But there is still some resistance. And how do you go around that remaining resistance? For me personally, I force myself to learn about their disciplines. You mentioned that I know a lot about biology. Well, compared to a biologist, I still don't, but compared to a mathematician or statistician, I do. So that's because I force myself to learn about biology. If I want to collaborate with them, right? If I want to collaborate with the biologists, I need to understand their language. Yeah. So I need to learn about their discipline. And you will be amazed that once you understand enough, okay, and during their discussion, okay, you can actually suggest one or two things that resonate with them, that they agree very well. Then they look at you differently. They think, wow, this guy is not just a statistician. He actually can think as a biologist. So maybe he can help me with my problem. because he thinks like a biologist. So I think that is important. It's like learning, how do you learn? Like learning a new language, basically. Like I believe that if you learn a new language, you have to, when you speak a language, right, you change your personality. Well, that's what I believe. You change your personality. So when I'm speaking English, I try to have a personality of an Australian or a personality of an Englishman, that is more kind of straightforward, less what do you call it, less bureaucratic, and I think it's the same with this cross-discipline collaboration. So we need to speak in their language, at least try to understand their language, and then when we speak to them, it's using the personality or the perspective of their discipline. But of course, I mean, we can never be them, right? I can never be a biologist, but if they see that you try, they will appreciate that very much. Imagine you have a Westerner, okay, a bule coming to Indonesia, that his English is poor. Sorry, his Indonesian is poor, so he speaks English mostly, but he tries his best to converse in Bahasa Indonesia. Then you will appreciate that very, very well, and you will, maybe even if you were angry with him in the beginning, you'll become much more friendly because you think, well, he's actually friendly, he's trying. So I think that, but of course, it also needs to come from the other side, from the biology side, right? We try, but they also must try for the collaboration to work. Because sometimes, so I don't always have successful collaboration with biologists. There are some biologists who never want to learn anything about statistics. And all they want is, here is the data, analyze it, give me some numbers and give me some tables. Well, I mean, I may do that for them once or twice, but after that, I stop because it's not going to work. You are not going to have a relationship with people who will never learn about you. So I think it needs to come from both ways. And I think lastly, my last point would be, in a place like Indonesia, where it's still very much a top-down kind of society. Maybe you can have a special kind of grand call, like hibah bersaing or something like that, where you force people to collaborate. So you need to put people from the different discipline in the grant. Otherwise, you're not going to get the grant. Something like that. Some kind of internal university kind of initiative. So if you say they need to put at least say 4 or 5 disciplines, if they don't, then it doesn't matter how good their grant applications, how good they are as researchers, they are not going to get the money. Because we have that in Australia, we have that. So that also forces people to collaborate. And after a while, you find that it's not that scary actually, because a lot of the reluctance to collaborate, I think people are scared. They don't know about the other side. Once they know about the other side, and it's not too bad, you will be amazed. They started talking. Thank you.
Thank you. So yeah, that's a really good suggestion. We at least we try to learn something new, so we never stop learning. And regarding the hibah, the research grant, it's happening now. I mean, we're seeing an increasing number of research grants that requires collaboration. In the local ITS level, they have provided this kind of grants, and also in the national level, that requires us to have a collaborator from different university even, and the field.
That's a very good thing. That's a very good.
Yeah. But maybe there is still a psychological barrier if you're not used to this yet, to start the actual communication with other people from different disciplines. Yeah.
Because So, no, sorry, you continue.
Yeah. So your suggestion was really good. So at least if we read a lot, we know what problems there are. Maybe we try to learn something new. That might actually help.
Yeah, and I think collaboration naturally, at least in the beginning, if you collaborate with people from other discipline, you will feel uncomfortable. That's just natural. It's for everybody. You feel unnatural, you feel scared, worried, sometimes you feel stupid. It's normal. But then what do you do after that? I mean, I have that moments, like I feel stupid for like, half a minute, like why I don't understand all of this thing, and all of these people just talking about it, like, like this is this breakfast conversation. Then I said, excuse me, I'm really stupid here. So you have to admit that you're stupid. I'm really stupid here. Can I ask a question? Then it actually clear, kind of a lot of things from my chest. I feel much better after that, admitting that I'm stupid. But again, that's cultural, right? In Australia, if you say that you are stupid in that manner, people actually don't think that you're stupid. But I don't know in Indonesia. I mean, maybe you have to use different approach. Yeah, because I never work in Indonesia. So after my graduation, I went overseas straight away within months. So in terms of the working cultures, I'm not really familiar. I think there is a possibility that if I work in Indonesia, I will offend a lot of people very, very quickly.
Thank you very much. Thank you.
Yeah. Okay.
Thank you. No. Thank you for letting me sharing kind of my experience, and I hope the students also learn from this, because in 10, 15, 20 years time, they will be the leader. I mean, we will be retired by then. So yeah, if they can learn something out of this, that will be very good.
Yeah. Okay. Any maybe last question from the students, because we are almost running out of time? No? Okay. Yeah, because there is no question from the students. Maybe in the last session of the discussion, maybe Professor Agus Salim can give the closing remarks for the session, and also after that I will close the session. Okay, please.
Okay, thank you, Dr. Dicky, and again, thank you, the other organizers. Yeah, I'm very happy to be able to share all my experience, both the lectures and the subsequent discussion that have taken place. And I hope we all kind of learn. I mean, I will learn as much as you guys will learn from this. And of course, one thing that I want to say is that if there is if there's any kind of wrong information that I have given unconsciously, and if there's something that I said that offended other people, I mean, I would like to apologize for that in advance. Another thing is I really have a lot of hopes for the young generation of Indonesians. Okay, and as I said, in 15, 20 years time, you will be the leader in the field that you're working. You will be competing with people from other nations. And we have a lot of potential. Indonesia have a lot of potential. Indonesia young generation have a lot of potentials. A lot of smart people in Indonesia. But throughout my experience working overseas for 21 years, what hold a lot of Indonesian back from achieving as much as people from other countries, for example, like India or China, is well, first is work ethics. Okay, it's so if there's one thing that I want to say to the students is that we need to change our work ethic. If we haven't changed already, we need to change our work ethics. Okay, we need to try our best in whatever we are doing. So that's very important. That's what have been holding our country back. That's what holding Indonesia back. We have to change our work ethics. We work harder to to bring better things for the country and to be able to compete with other nations. I mean, it pains me that we cannot even produce a decent COVID-19 vaccine and other countries can. That's very bad. Now you will be the leaders. It will be too late for my generation, but you will be a leader in 15, 20 years time. Don't let that happen to your generation. We must be independent. Okay, so sovereignty, the Indonesian word is kedaulatan. I mean, it has a lot of meaning, and one of the meaning is kedaulatan in this area, in science. We need to be independent in science, sufficiently independent, so that we are not under pressure from other countries all the time. Okay, how can you be independent and sovereign if you're not sovereign in your science? People they will take over easily the country because we have no experts in critical areas, right? Okay, so that's one thing is work ethics. Secondly, I think what has been holding us back is we are not confident. So that's another thing that I want you as young generations to change. Okay, be confident, percaya diri. Okay, percaya bahwa Anda bisa, that you can do it. Okay, as a nation you can do it. Yeah, because we are not worse, or the Chinese and the Indian are not smarter than us. I can tell you that because I have Indian students, I have Chinese students, I have Iranian students. They are not smarter than us, okay? But what they have more than us: first, better work ethics; two, better confidence. I mean, we don't have that. Well, some of our students have, but on average, our students don't have that. Okay, thank you, Pak Diki.
Thank you very much for everything, Professor Agus Salim, for your time in giving the presentation and also discussion today. We believe that it will be beneficial for all of us. Okay, thank you very much. I will return the forum to Bu Vivi. Monggo Bu Vivi.
Thank you very much for Professor Agus Salim for the excellent lecture today. And thank you for Dr. Diki for conducting this amazing session. Furthermore, we would like to present a certificate awarding to Professor Agus Salim as our speaker today.
What am I supposed to do? Take a screenshot?
You're supposed
If
to
you would like to, Professor, that's okay.
You can email the picture to me. Thank you.
Sure.
But we'll also send you by hopefully.
And also to Pak Diki as our moderator today.
Thank you very much.
Okay, before we end our lecture today, we invite you all the participants as well as the honorable of speaker and moderator to take a group photo. So for the participant, please turn on your camera. Okay, all right. I will count 1, 2, 3, smile. Once again, like the next slide. 1, 2, 3, smile. Okay. Next, 1, 2, 3, smile. Okay, we have taken a group photo. Then for the participant, please fill the feedback from through the link at inti.it/GLP feedback 2021 that you can also see on the Zoom chat room. Finally, we have reached at the end of today's global learning program. We sincerely apologize for any mistake we may have made in presenting Master of Ceremony and Committee. Thank you very much to Professor Agus Salim as speaker today, and Pak Diki as our moderator today, and all the participants for the attention and cooperation. We will see you in the next global learning program. Good afternoon and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you very much for Professor Agus Salim and
Thank you.
Pak Diki Atsukia.
Thanks everyone, and yeah, hope to see you again soon.
Yeah, hopefully we can.
Thank you, sir.
Bye bye.
Thank you.
Terima kasih. Terima kasih Pak.
Sama-sama. Makasih.
Pak Diki. Terima kasih.
Okay, thank you everyone. Let me end the session in a 5, 4, 3, 2, 1. Thank you.